Okay. So basically, you took your piece of paper, you folded it so that you had 2 doors, and then you cut across so that you have 4 doors on each side. Okay? What we're actually going to do is we're actually going to start, once you guys have finished cutting, with some important vocabulary on the back side of the paper. So when you're done, you can turn over there and just give us a minute, because I didn't have enough scissors for 1 per person. So again, once you've cut, we're going to start with some vocabulary on the back. And we're only going to fill in one of these doors today, because it's going to focus on the one function that we've studied, which is the absolute value function. Okay? The other doors are going to be for different functions that we study throughout the course. And there are even more than 7 more that we have to learn. But those are going to have some other things that we're going to organize them with. So just be aware. Okay, on the back side, basically everything we're going to write about on the back side of this is transformations. So remember how we looked at the parent function for the absolute value? It was that first one in the chart that was filled in for you. And then you graphed all, like 6 more absolute value functions, and you recorded how they were changed. Okay? What you were really looking at is you were really looking at transformations. You were really looking at, you put in a number into the equation, and what it did is it took the parent function, it kept that same shape, but it transformed it somehow. Maybe it flipped it upside down, okay? Maybe it made it wider or narrower, okay? Or shifted it up, down, or left and right. All those things are transformations, and we kind of touched on this a little bit. You learned transformations in geometry, those actions like reflection and rotation, different things like that, okay? So the first one we're going to talk about is translation. So underneath the topic of transformations, the first specific one we're going to look at is translations. So on the back side of your organizer, the first thing you wrote was transformations. And then underneath it, we're going to talk about translations. There's 4 in total that we're going to talk about. So you have the back page to talk about those 4. I wrote this small, and I had all that extra space at the bottom. So should be okay. What is translating something? Yes. Good. Taking the graph as it is, no flipping, rotating, anything like that, just sliding it on the graph to a different location, right? So in case you don't remember that, you can think of it as shifting, okay, or sliding along the graph, but there is no rotating or flipping or anything like that involved. Now, you guys saw, what did that in the absolute value problems? What things shifted your graph from the parent function? Say it louder for them to hear. Good. The h and the k values shifted them. Now, one was in control of one certain kind of shift, and one was in control of the other. What did the h control? Oh, I see some people going like this. Yeah, along the x, okay, the x coordinate of the vertex shifting left and right. So when the h, or the number that's happening inside the function, remember that had to happen inside the absolute value bars for it to be considered h, or a shift left or right. So the way that we write that is we write the h value happening with the x within the function. So all this means is that the h is going to be with the x inside of the function. So if it's a square function, x plus 3 will happen all inside of the square. If it's an absolute value function, x plus 3 is all going to happen inside the absolute value bars. If it's a square root, x plus 3 is all underneath the square root, okay? Whatever type of function you're working with, this plus h or minus h value is with x inside of that function, okay? So this type is going to shift left and right just like we saw with the absolute value. Sorry, my handwriting is not very good. Okay. So if we wanted to shift up or down, was that k value from our absolute value function, was it also inside the absolute value bars? No, it was like once you're done with the absolute value function, right? Then go add or subtract this extra amount. So the stuff that shifts things up and down happens as a plus or minus, but it happens once you're done calculating the function. So after the square root's been calculated or after you've squared something, it happens afterwards. So the way we would note that is you would use the function, whether it's the absolute value function or a radical or whatever the function is, and then after the function is done, it would have this other value being added or subtracted to it, okay? And so that's going to cause our shifting up or down. And then what I'll do is I'll give you guys, you can just jot next to each one of these, an example of a function and what it would look like in the function. Okay? So an example of one of the parent functions that we're going to learn about, you guys have seen it in Algebra 1, but we haven't done it yet in here, is the quadratic, okay, or a function where something's being squared. If I wanted to shift this function left or right, I would want the value to be added or subtracted where the x is all as part of what is being squared. So the way I would change the right-hand side of this function if I wanted it to shift left or right is I would add or subtract some amount inside of the function with x, something that would be done to x before I executed the absolute values or the square root. Okay? So this would shift 2 to the left, okay, because of the whole minus h thing like we talked about with absolute value. If instead I wanted to shift the function 2 up from the parent function, I would have the complete function, and then after the squaring was done, I would say something like plus 2. Does that make sense between the notation? So this is just, it's happening to x within the function. This is happening after that specific part of the function is complete, okay? And that will cause your shifting up and down and left and right. Yes? Oh, I just picked 2 as an example. Yeah. So if I wanted to move it specifically 2 spaces, you could pick whatever number you want. I just wanted to show you the difference between when it would be a horizontal shift. It would be happening inside of the square with the x, whereas when it's a vertical shift, it's happening after the squaring of the x is already done. Okay? All right. Any questions that you guys have on translations? Now, you guys aren't going to have to use these words on the test tomorrow, but we're going to start using them. I'm going to start using them for every unit after this. Okay? All right. The next transformation that we're going to look at besides a translation is a reflection. Okay? So what does a reflection do to an image? Wait. Okay, it mirrors it. So essentially, there has to be something that you're kind of mirroring over or through. Okay? So, for example, in geometry, if you guys did a thorough job on translations, which depending, you may or may not have because it's not as big of a standard before as it is now. But if I had this triangle, okay, one reflection of it could be down here, okay? Would you say that that's kind of a horizontal change or a vertical change for that triangle? It's a vertical change, but what did I reflect over if you had to name the piece of the graph that I reflected over? The x-axis. So kind of weird that a vertical reflection actually goes over the x-axis, but it's because it goes from top to bottom, okay, or from down to up. Whereas if I had drawn the image of the triangle over here, okay, that's more of a horizontal reflection because it's gone from being on the right side of the axis to being on the left side of the axis. But what did I flip over when I reflected that time? The y-axis, okay? So first of all, understanding that a reflection is like mirroring the object, like a mirror image, or like flipping the object, okay? Understanding that type of movement. And then again, how do they note it? And again, there's ways you can do this horizontally and vertically, okay? So if we put it inside of the function with x, so negative is going to cause our reflection. You guys saw this with the absolute value function. Remember when you graphed all the functions, there was one of them that was a downward facing v? And why did that one face down? Because the a was negative, right? Because there was a reflection going on there.
Why is it on the outside of the f? I mean, wouldn't it be, without absolute value, it would still be regular?
Yes. So that's why in absolute value we would only look at vertical ones, but there are other functions where we can then note it as horizontal. And later on we'll see the relationship between the two. Like sometimes a vertical stretch looks the same as a horizontal compression, and we'll talk about that idea. Okay. So for the reflection here, okay, if the negative is affecting the function inside, okay, with the x value before you've calculated the function, anything that's happening to the x is a horizontal change, like our h was a horizontal change. So this is a horizontal reflection. But again, when you reflect horizontally, so like from left to right, what are you really flipping over? The y-axis. So this reflection is going to reflect over the y-axis. If I put the negative in front of the entire function, and this is what you saw with the absolute value, we saw a negative out here. Okay? If I put the negative in front of the entire function, it's not inside of what's happening. Then out here it's a vertical change, just like how the k happened kind of separate from the function. Okay? So this is going to be a vertical reflection. But when it's a vertical reflection, what am I flipping over? The x-axis. Okay, so this is going to reflect over the x-axis. So you might think, well, those things don't look different. So the example I'm going to use here is actually a linear function. And we'll come back to these at another time and discuss the actual images of them. But let's say I just had the line 3x plus 3. So that would be a line on a graph, a y-intercept at 3, and a slope of 3. Okay? If I wanted to reflect that line over the y-axis, okay, I wanted to do a horizontal reflection, all I would be doing to the function is just applying the negative in the term where x is. Okay? So that would end up looking like negative 3x plus 3. What's the only difference between that and the original function I had up there? The slope, okay, is just negative instead of positive, which means the lines would cross like this, right? Okay. So do you see how that would be a reflection over the y-axis? If I had the y-axis going down the middle of my arms right here, that if you folded them over, they would sit on top of each other if they had that same y-intercept but opposite slopes. Okay. If I want to perform a reflection over the x-axis, then what I would do is I would apply the negative to the whole entire function after it's already been used. It's not just being plugged in where x is. So what that would look like is a negative being applied to the entire 3x plus 3, which then looks like negative 3x minus 3. Okay? Notice in this scenario, both the slope and the y-intercept change, because if I had a line like this, right, and its y-intercept was up here, and I wanted you to flip it over, okay, that x-axis, your y-intercept should end up on the other side, down below. So instead of at positive 3, now it's down at negative 3, like its mirror image. Okay? And again, you'll see more and more of this as we go through the different types of functions. Okay? All right, the last change we're going to talk about today, and then we're going to add a fourth one on another day, is we are going to talk about vertical stretching and compressions. And in comparison to our absolute value graphs, when you think about this, okay, we saw the reflection. When we saw the a value turn negative, we saw ourselves reflect over the x-axis. So we saw that vertical reflection. We saw the h and the k, or the translation, horizontally and vertically, when we changed the h and k values. Okay? But what we haven't talked about yet is how the graph sometimes got more narrow or more wide, depending on the a value that we put in. Okay? So if the a value is negative, we knew it flipped it over, right? That's the reflection part of it. But the number part of the a value changed how narrow or how wide it is. So in your vertical reflection, okay, it's only about, notice that it's only vertical this time. Everything else we did so far had a vertical and a horizontal, and that was whether we put it inside with the x or without the x, right? Happening before or after the function was done. Since this is only vertical, we're only talking about some number affecting the function, not inside of the function. Remember how we did absolute values, and every time we factored the number out that was in the parenthesis inside the absolute value bars if we didn't want it there? Like if it had a 2x inside the absolute value bars, we factor out the 2. Okay? So every time we saw this a value out in front of the absolute value bars. Okay? What happened if the a value I'll say the absolute value of the A value because we already know if it's negative, that's causing the reflection part. Okay, we're going to treat that separate than the actual numerical part. If the A value was greater than 1, what was happening to our graph? Okay, becoming narrower, the lines were steeper. Would you guys call that, if I was going to take the graph paper and I can only adjust it vertically, so all I could do to your paper was I could crunch it or stretch it, okay? If the V was getting narrower, okay, or steeper, would that have to come from stretching the paper vertically or compressing it and shrinking it down? Stretching it out, right? So when A is bigger than 1, and we're talking about an A being a number out here, okay, before the function happens, when it's greater than 1, this is considered a vertical stretch, just like you guys just said. It would make it steeper, which if I could only adjust the paper vertically, I would have to stretch it out like that. Okay? If the absolute value of A is less than 1, and since we said absolute value, it's going to not go lower than 0, okay? That means that the V would then go and it would get wider. So that means I'd have to take your paper and I'd have to like crunch it together so that the V would be pushed apart wider and wider. Does that make sense? Okay. So that's what we would call a compression. Notice I was only talking about vertical movement of the graph, right? So this would be our vertical compression. So you guys should actually be able to give me the examples in this sense if we use the absolute value as the parent function. Can somebody give me an example, if this is my parent function, absolute value, of how I could change that equation to show a vertical stretch from the initial parent function? What would I change on the right side of the equal sign instead of just having the absolute value of x? What's that? Okay, but what does A have to be? Give me an actual physical number that would represent. Okay, good. So 2 is an example. If I use 2 there, that represents a stretch of that parent graph. Those lines in that absolute value function are going to be steeper. The V will look narrower. Okay? Can somebody give me an example of compression if I'm using the absolute value function as my parent function? Yes. Good. So 1/2 or 0.5x would be an example of compression because that would make the slopes of those lines less steep, or it would be a wider V. Okay. All right, any questions? We're just going to use this basically to keep track for us of all the functions we learned. So what you want on the front door is the name of the function and what the parent function is, the equation, and what the graph looks like, okay, so that you have the basic shape. So on that first top left-hand door, I just wrote absolute value function. And then at the bottom of it, I wrote what the parent function was. So I could just kind of remember how the equation was structured. And then what I did was I graphed that parent function. So what does an absolute value function look like? What's the shape of V? For this parent function, when it's just the absolute value of x, where should the vertex be? 0, 0. And what should the slopes of the lines be? Good. 1 and -1, so you can show those. It doesn't have to be super specific. We're just looking for general shapes so that we understand the idea. So that's all I have on the front of the door for the absolute value function. So it just has the name, the parent, and what the graph looks like. Okay. Then when I open up the door, okay, I have 2 sides. Can I change? Does anybody still need this? Okay. When I open up the door, I'm going to have 2 sides. On one side, I'm going to write kind of the general form of the equation and an example with its graph. And on the other side, we're going to talk about those transformation things, okay? Good. Okay. All right. So I'll use these as my 2 sides when you open the door, okay? So here's the open door, and then here's the side that's like inside the handout, okay? Is that good with everybody? All right. So the first thing, and I would write kind of a little bit small. to fit it in the door. I would write how we visualized the absolute value graph, and then I'm going to write an actual equation with numerical values, and we're going to graph it. So this is going to be just a little review for you of graphing absolute value functions. And then we will just use, I tried to make the numbers not too horrible, the rest of the space on the door to build the graph. All right, so somebody tell me a characteristic of the graph as I expect to put it in here, because we should know. I'm taking a test tomorrow that would include us doing this by hand. Yes, Annika. Good. This graph is going to open downward, so I should expect to see a downward V when I'm done. What else? Yes. Good. So the vertex that we're getting from the H and the K values, and your vertex should be at -1, -3. So -1, -3. My V should be downward, so I'm prepared to fill that in. Now I just need some points guiding those lines that are on the side. So how am I going to complete my graph? Okay, so a slope of -2 from our vertex point. So that means down 2 over 1, and also mirror that or go down 2 over 1 in the other direction to be able to form that absolute value graph. So that shouldn't be new to us. That should be review. On the other door, how we're going to be using this in the future is that you're going to list the transformations that occurred. Okay? So I'll give you a small hint. You should account for everything that's here. And when I say account for everything that's here, that means everything that's there that's different than the parent graph, which means this whole adding 1, subtracting 3, multiplying by 2, and having a negative. I should list a transformation for each of those changes that have been made in the parent graph. So someone tell me one way that this graph has been transformed from the parent graph. Yes? Okay, good. So would we call that a vertical reflection or a horizontal reflection? We went from up to down, so we had a vertical reflection. Okay. All right, what's another transformation that took place? Yes? Okay. Be a little more specific. We did have a translation. Okay, so we moved to the left 1 and down 3 for our translation. Okay. So we've taken care of 3 aspects so far. We've taken care of this multiplying by the negative. We've taken care of the 1 and the 3. The only thing we haven't taken care of is this coefficient of 2 in front of our absolute value. So what is that doing to our graph? Yes? Good. It's making it more narrow because the slope is bigger. So look on the back of your organizer. What are we officially going to call this now? Yes. Good. So it actually has a vertical stretch of 2, okay, by a factor of 2. Okay. So it has a vertical stretch by a factor of 2. And that would sum up all of the transformations that have taken place. Okay?